All right, so what I want to do today is I want to talk a little bit about convergence of Fourier series. So what are the two big theorems we're going to do today? For convergence of Fourier series, what are the theorems we're going to do? Dirichlet's theorem for convergence and Fejer's theorem. Right. Normally I don't care how you pronounce people's names, but if they're mathematicians, they do have to be pronounced properly. What mathematician's name does not rhyme with orange? Or maybe it does. No, which? Lagrange. Right. That's the one word you can use that rhymes with orange if you get stuck. Lagrange. Not Grange, Lagrange. Okay? So, what is the difference between Fourier series with Dirichlet's theorem and Fourier series with Fejer's theorem? What's the biggest difference? What's the difference between the two series? Are the series the same, or do we do something different for the Fejer series than we do for the Dirichlet series? If you don't know this, you have not read the book enough. Yes?
Divide by n in the Fejer series?
Not quite by n, almost by n, close. So in the Dirichlet's theorem, you have the regular Fourier series, the Fourier coefficients are unweighted. In the Fejer series, you introduce these very slowly varying weights, 1 minus n over big N, or big N minus n over big N. So what is the effect of these weights? What does it do? It greatly changes convergence properties. And when you think about what's going on, you have the weights, so when little n is getting very large, then the weight is becoming small. So the contribution is mostly coming from the smaller from the smaller index n in the Fourier coefficients. Now, as big N grows, more and more Fourier coefficients come into play. So Zizi, you want to try turning off the lights? And we'll see if that makes it view a little bit better on the board. Just push something down. There we go. All right, so what I'm going to try to do, and I'll do it in such a way that it doesn't move, is here is a plot of, I'm approximating the function that is defined as follows. So I'm doing a step function. It is defined as -1 if x is less than 0 and 1 if x is greater than 0. So this has a discontinuity. So according to Dirichlet's theorem, this is not going to converge point-wise at the origin. Well, actually, we technically don't know that. Dirichlet's theorem just has nothing to say about what happens at the origin. It may or may not converge. We don't know. Fejer's theorem says it should. Does Fejer's theorem say anything? Or do we assume continuity in Fejer's theorem? I think we assumed continuity in Fejer's theorem as well. And so what we can do now is we can try to get a sense of how well do these theorems behave. Let's expand things a little bit. All right, so here is I'm going to look at approximations. So this is one approximation, 2, 3, 4. And so this is what's happening as I'm using Fejer series. Does this look like it's doing a good job approximating our step function? I'm sorry? How is it doing at the origin? Good job, bad job? Is it getting the right value at the origin? Well, I haven't really defined the function at the origin, but if the function is positive 1 on one side and negative 1 on the other side, it seems like this is a pretty good definition. So I might have actually miscoded things to have the negative of the function, not a big deal. You would expect that it should be converging to 0 in between. What else is interesting? It's interesting looking at this region over here just before 0 and just after 0. How big is that? As we take more and more terms, does it get smaller or larger? So over here, it does look like as we're increasing the number of terms that the width where I'm having an issue is getting smaller. I don't know if it will let me just plug in 200 here, or if that's going to just blow things up. So it's thinking now about trying to do that many terms. Okay, it was able to do it. The red just means I'm going beyond Mathematica's manipulated and it's not happy, but it's still willing to do it. And you can see the width does shrink. So this is not even close to a proof, but it looks like the Fejer series has really good properties here in terms of convergence. Let's look at what's going on now with the Dirichlet series. So I'll make the picture a little bit larger. And so again, I'm going to increase the number of terms. Does that look similar or different from the Fejer series? Yeah, a lot more oscillation, right? But now what's happening to that oscillation as we increase the number of terms? Yeah, it seems to be canceling, so the oscillation isn't so bad. But there is something that is not canceling. What do you notice that's surviving?
The amplitude at the ends.
Yeah, the amplitude at the ends. It's called the Gibbs overshoot or undershoot. So Gibbs was one of the first American scientists of note, spent almost his entire life in New Haven, which is also noteworthy. And he was one of the first people to investigate this overshoot in the Fourier series. Now look at what's going on at the origin. By symmetry, it's got to be doing the right thing at the origin, right? It's being pulled one way by one side, one way by the other side. On average, it does the right thing. But it does this by overshooting then and then coming back because of its oscillation. So this shows you how wildly different the Dirichlet convergence theorem can be from the Fejer convergence theorem, or the Dirichlet series, the standard Fourier series from the weighted. This is a general principle in mathematics. Frequently, the more weights you introduce, the easier the analysis becomes and the better convergence results you get. You no longer have the most natural object to study. You might want to study just the Fourier coefficients. That's the natural quantity. It turns out the analysis is easier if you put in the weights. All right, so what I'm going to do next is I'm going to look at the absolute value function. So I'm going to define the function to be the absolute value of x minus a quarter. The reason I'm putting in minus a quarter is just so that it will now integrate to 0. And so now when we come down here, here is the Fejer series approximations. I'm going to make that a little bit bigger. Move this down a little bit. And now, how do you think the Fejer series should do for the absolute value of x? Good job, not good job. What do you think? What's the condition we need for Fejer's theorem? Continuity. We've got continuity, right? So there should be no problem here in terms of approximating the absolute value function. And we see that there's no problem at all with the approximation. Let's turn to our friend Dirichlet. How do you think Dirichlet should do? What condition do we need in Dirichlet's theorem for good approximation? In the book, what did we use for Dirichlet's theorem? We need it to be differentiable at the point. Is the absolute value function differentiable at the origin? No. So does Dirichlet's theorem have anything to say for what's going to happen here? No. Let's see what happens. Let's see if we get the strange oscillation we had from before. I mean, if you look at this, I think it's a little bit more oscillating than the Fejer one, but still very quickly. How's it looking? Okay. All right, let's bump up from 50. We'll go up to 100. I think I can do 100 without too much trouble. All right, how's that looking? Pretty good. All right, hopefully you get the point. That looks pretty good. That is the absolute value function. Why are we getting good convergence here? We're not in a condition where Dirichlet's theorem applies. What's going on? So can you turn on the lights? Thanks. So what's going on? Why are we getting such good convergence? So what did we use when we did the proof of Dirichlet's theorem? What was the key fact we were assuming about the function? And this was already said a moment ago. Differentiable. So is the absolute value function differentiable? Most of the time, but it's definitely not differentiable at one point. So how badly, oops, are all the lights on? Okay. Oh, it just seems a little bit darker than normal. So, yes?
Was it workable because it's differentiable everywhere except at 0, and at 0 the two sides converge to the same point?
So say that last part. The two sides
are coming to the same point.
Well, but you have a different left derivative and a different right derivative. But both the left and the right derivatives exist. So the key fact is that even though the function is not differentiable, it's what's called Lipschitz with exponent 1. So the real thing is you want a bounded quotient. And so the limit as h goes to 0 of f of x plus h minus f of x over h in absolute value, this was at most b. And because this is at most b, we can actually do the analysis as was discussed in the book. And everything is going to hold. We actually did not need differentiability. All we needed is that f of x plus h minus f of x was less than or equal to some constant times h to the alpha, where alpha was greater than or equal to 1. So this is a poor man's this is the equivalent of differentiability. Or maybe not equivalent, it's a substitute. What would I need this exponent to be for the function to be differentiable? So what would give me differentiable? I'm going to try to zoom in a little bit now. So to give me a condition on alpha that will imply f is differentiable.
0.
If alpha is 0, then it tells me that this quotient is going to be bounded by a constant. When I divide by h, this could go off to plus infinity. So if I take alpha equals 0, this quotient could blow up. In order for the function to be differentiable, I need this quotient to stay bounded and, in fact, to converge to a number. So if it's strictly greater than 1, the derivative will be 0 at that point. Because then the numerator is going to look like a power of h that's a little bit greater than 1. If the exponent is exactly equal to 1, in some sense it's very close to being differentiable. And so for a lot of problems, this is a close enough equivalent. It really gives us the properties we need to make the arguments work in terms of all the estimation. We don't need the full strength of differentiability. We just need some way to control the size of the quotients. Okay. So what I want to do now, just see. No. All right. In case that's making it darker over there. So what I want to do now is I want to go through the proof of Fejer's theorem, go through the proof of Dirichlet's theorem, try to highlight the key ideas, and try to talk about where in one of those theorems I was trying to slip something past you. Did anybody find the place where I was trying to slip something past you? Any thoughts as to where that was? Any thoughts?
I had a thought.
Yes.
Did it happen to be in Fejer's theorem?
No. So now at least you know which theorem it's in, right? That's the advantage of only having two options. All right, so the first is an approximation to the identity. And this is a wonderful concept. And so I'm not going to go into full detail about all of this. This is something you're supposed to have read. The idea is a unit point mass. So for instance, here's some point. Let's take the origin. We might take a triangle function like this, go to 1 over n here, minus 1 over n here, go up to height n. The area under this is going to equal 1. And in the limit as n goes to infinity, I'm basically getting my mass of 1 spread out over a smaller and smaller region. And so there's three properties that an approximation to the identity should have. It should integrate to 1. Basically, it's a mass. It should be non-negative. Okay, you can't have regions where you have negativity. And then you give me any epsilon, and I can choose either a delta or some n, such that as long as I'm not too close to the point of behavior, for all sufficiently large n in my sequence, the integral is going to be arbitrarily small as long as I stay away from that very close neighborhood of the origin. So typically you'll have a sequence of functions, an of x, and you'll have, for all epsilon, there exists an n naught. such that the integral, say, absolute value of x greater than delta of an of x dx is less than or equal to epsilon for all delta. And of course, my n naught will depend on delta. So you specify a small little window about the origin. Eventually, the integral outside that region becomes negligible. So let me explain a little bit about why approximations to the identity work so nicely. Here's 0, here's minus 1 over 2n, here's 1 over 2n, and here's the function that's going to be n over here and 0 everywhere else. So in this approximation, it's not going to be continuous. You can do everything with continuous functions, it's fine. Let's look at the integral from minus infinity to infinity of f of x, and we'll call this function an of x. Well, the only part of the integral that matters is the part from minus 1 over 2n to 1 over 2n. So this is the same as integrating from minus 1 over 2n to 1 over 2n f of x times the function n dx. Now, if we're going to make more progress, we need to assume certain things about our function f. So when you take a class in measure theory, you often say it's enough to study certain classes of functions. If I can understand what's going on for these functions, I can then build up other things from them. What's a good class of functions to look at? Now, if you had to choose a class of functions to look at, what class would you choose? Well, constant functions is not rich enough. Differentiable functions. How many times differentiable? Infinitely many would be nice, but that's a little overkill. So maybe we'll assume our function differentiable and closed bounded interval. Maybe let's just assume f of x equals f of 0 plus some constant plus an error of size x. This is like the beginning of a Taylor series approximation to our function. If you think about what's going on, if our function had a Taylor series, f of x would be f of 0 plus f prime of 0 times x plus dot 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 dot. I don't really care about the size of this. I just care that the error is at most a constant times x. So you can quantify exactly what it is. Does my function have to be differentiable for this to hold? Or would the absolute value function work here? The absolute value function would work here. I don't need differentiability. That's why I'm trying to be a little bit, vague here. I could assume my function is twice differentiable. I would have a Taylor series expansion, that'd be fine. I could assume my function is once differentiable. I could use the mean value theorem. I don't even need that. Lipschitz with exponent 1 would be sufficient here. And now if I look at what's going on, this integral becomes, well, I integrate f of 0. What do I get when I integrate f of 0 from minus 1 over 2n to 1 over 2n and multiply by n? What will I get? I'll just get f of 0, because I have a window of size 1 over n times n. So I'll get f of 0 plus an integral from minus 1 over 2n to 1 over 2n, n times an error of size x. And again, I'm being a little vague because I just want you to get the general idea. When I integrate something of size x, I get something of size x squared. My interval is of size 1 over 2n, so the largest I can be is at the endpoints. So that's going to be something of size 1 over n squared. I multiply by an n. How large is the contribution from this piece? 1 over n. So that I basically get f of 0 plus an error of size 1 over n. And so this gives you an idea of how approximations to the identity work. The idea is that as n gets very, very large, when you integrate a function against an approximation to the identity, it essentially just returns the value at the origin. I could, of course, shift the approximation to the identity, and instead of looking at an of x, I could look at an of x minus a half. And then I just shift all the action to be happening at 1/2. Okay? So in the limit, as n gets very, very large, this is going to converge to essentially what we'll call the Dirac delta functional. And so we just define the integral minus infinity to infinity of f of x delta of x minus a dx to be f of a. It's essentially saying, imagine you have all the mass concentrated at point A. These are extremely useful to look at. Now this is, of course, not a continuous function. This is a function which is plus infinity at A and 0 everywhere else. It's an operator. You give me a function, and this shoots out the value of the function at the point A. So if you take a class in functional analysis, you can look a lot more at stuff like this. This is a very convenient thing to work with. If you want to do things very carefully, a good way to do this is through the approximations to the identity. And that allows you to get your hand on stuff like this. And that's the main difference between Fourier series that we use in Dirichet's theorem and the Fourier series we use in Fejer's theorem. One of them, we have an approximation to the identity. The other, we don't. And so, just so I don't get this stuff wrong, so the Dirichlet kernel, so this is dn of x. It is the sum, n goes from minus n to n of e to the 2 pi I n x. And this is going to be the sine of 2n plus 1 pi x divided by, I dropped what it was divided by. Is it sine pi x? That sounds right. And the other one is the Fejer kernel. And there, fn of x is going to be 1 over n, the sum, n goes from 0 to n minus 1, dn of x. That's going to be n minus the sum, n goes from minus n to n, of n minus the absolute value of n over n, e to the 2 pi I n x. And this is going to equal sine squared of n pi x over n sine squared of pi x. Okay, so these two kernels are extremely different. The reason they're so useful is that if I integrate my function f against dn of x, or if I take the convolution, I get back my Fourier series. If I take the convolution of my function f with the Fejer kernel, I get back a weighted Fourier series. So the convolution is an extremely useful object. If you read the probability chapter, it might have been mentioned there. So convolutions. If I give you two random variables and they have densities, f and g, then the density of the independent sum x plus y is the convolution of the densities. And so here, if I look at the integral, I'll define it this way, f star g of x is the integral from 0 to 1, say f of t g of x minus t dt. And if I look at f star dn, I get the Fourier series. And if I look at f star f of n, I get the Fejer series. In some sense, this should be clear. If one of them holds, the only difference is I've added essentially these weights. So I can do the convolution in both cases. The question is, which convolution is better to do? Is it better to look at the Fourier series or the Fejer series? Well, a lot of it comes down to the integral we need to do. So if I want to look at, we'll call Tn of x, sometimes I might write Tn f of x, to just really remind ourselves we're taking the Fejer series associated to f. This would be the integral from 0 to 1 of f of t fn of x minus t dt. I want to evaluate this integral. Well, as n gets very, very large, if this is an approximation to the identity, what does this integral look like? So what should this integral look like? If the Fejer kernels are an approximation to the identity, what should this become?
Or fx.
So all the mass is concentrated when t equals x, so it should just look like f of x. That's why I wanted to do that quick calculation beforehand. If the Fejer series, if these are approximations to the identity at the origin, then this integral should just look like f of x. Hey, that's what we want to get. And that gives you some idea of why this should be converging nicely to the function. Because we're convolving it against an approximation to the identity. What's nice is when you do the calculation, we're going to just get some kind of Fourier series. Why? Well, the integral will be the integral from 0 to 1, f of t. And then I have a sum, n is less than or equal to n in absolute value, n minus the absolute value of n over n, e to the 2 pi I n x minus t dt. So when you look at what's going on here, I'm integrating with respect to t. I can pull outside the e to the 2 pi I n x, right? And I pull out the e to the 2 pi I n x. Great. What do I do about the integral and the sum? So I have an integral of a sum. What do I do? Interchange them. Why? It's finite. So whenever it's finite, you don't have to be too concerned. So here I've got the sum n less than or equal to n. I can move the sum outside, n less than or equal to n. And now I'm going to have the e to the 2 pi I n x. I have my n minus absolute value of n over n. And now I have f of t e to the negative 2 pi I n t dt. That's the definition of the Fourier coefficient. So then I'll just get f hat of n. And you can see this is going to give you a weighted Fourier series. That's why these convolutions are so nice. And if you look at it, the only difference that really would happen is, if I use the Dirichlet kernel instead of the Fejer kernel, I wouldn't have these weights. I would have something very similar without that over here. So the whole subject comes down to, do I want these weights here? If you're programming things, is it that hard to do this extra multiplication? No. Is it that hard to look at a weighted Fourier series rather than a Fourier series? No. But philosophically, if you're trying to study what's going on, do you want to look at the weighted series or do you want to look at the Fourier series? I'd rather look at the Fourier series. The Fourier series doesn't have as good convergence properties. And there's all these big questions. When does the Fourier series converge to the function you start with? What conditions do you need to assume about f? There is I don't know if I'd call it a beautiful example, but there is a function that's integrable where the Fourier series does not converge almost everywhere to the function. It turns out if your function is in L2, then you converge almost everywhere. And this was a huge theorem. And so if you assume even more, if you assume continuity, it's not that bad, and that's Fejer's theorem. And it all comes down to this is an approximation to the identity and how we handle it. So let's look now at Fejer's kernel and Dirichlet's kernel. And so hopefully now it'll be a little bit clearer why we want to look at these things as carefully. If this were an approximation to the identity, then the argument over here wouldn't be so bad. So again, I'm trying to decide how much detail to get into in class. If I'm not going into enough detail, either speak up now or just fake it for another 20 minutes and send me an email privately later. Okay? I'm going to assume at this point that if you haven't already read the notes on the proof of Fejer's theorem, you can now go back and follow the algebra. We want to show that the Fejer kernel is an approximation to the identity. We need to show three things. It's non-negative, it integrates to 1, and that if you stay outside a certain regime, the mass goes to 0 as n gets large. So the first thing is, does it integrate to 1? Well, if you look at what's going on here, we have a sum of exponentials. Each exponential, when I integrate from 0 to 1, is going to integrate to 0 except for which exponential? N equals 0. And when I take n equals 0, oh good, I've got 1. So it does integrate to 1. The next thing is it non-negative? Okay, well, e to the 2 pi I n x is sums of cosines and sines. I've got to do that. I've got to put in these weights, and then I've got to show that that weighted sum of sines and cosines is never negative. Is that pleasant or unpleasant? Unpleasant, right? It would be hell to look at this directly and show this is non-negative. There's an easier way. Not coincidentally, we have a formula written for what that sum is immediately below. Is it easy or hard to show that this is non-negative? Yeah, we've got a ratio of squares. What is the only difficult point? X equals 0. So as x equals 0, if we Taylor expand the numerator, we get sine squared n pi x. So the numerator is going to look like n pi x squared, n squared pi squared x squared. Down below, it's going to look like n pi squared x squared. Okay, so near x equals 0, it's going to look like n. That's great. This is exactly what you would want for an approximation to identity. It's really large at the origin. As we move away from the origin, what happens to this function? What happens to this as we move away from the origin? So we've got sine squared n pi x divided by n sine squared pi x. And let's say x goes from minus a half to a half. So as x goes all the way up to minus a half, this is going to sine squared of pi halves. That's going up to plus or minus 1.
So it's going to be bounded by 1 over n.
So it's going to be bounded by 1 over n. Right? So as long as we stay away from the origin, the numerator is going to be bounded by 1. And then the denominator, if I stay x is at least x naught an absolute value, the denominator is going to be at least sine squared pi x naught, if not larger. And the reason is, as we move away from the origin, the sine function is increasing. So the denominator is getting smaller. So if you just tell me I stay at least this far away from the origin, my denominator is now bounded, and then I have this whole thing is going to be a constant divided by big N. As big N goes to infinity, it's going to go to 0. So this proves that the Fejer kernel is an approximation to an identity. So again, I'm trying to prepare you for grad school where they're not going to go through all the steps. I did more even on the board than they would do in grad school in terms of telling you. All right? So it would basically just say, show that this is an approximation to the identity. Why are we able to get an identity like this? We have geometric series. And we can play games with geometric series. Now, in terms of evaluating this, what makes this hard? We've got these weights over here. But we also have this as a sum of weighted Dirichlet series. And we can put exponentials in over here. And when we put exponentials over here, notice that the denominator is always fixed. And then the numerator we can write as 2 exponentials and play geometric series games again. Okay, so it's a lot of geometric series identities to prove stuff like that. It's a good exercise. I can't remember what mood I was in when I assigned homework as to did I assign you guys to do that or not. Did I? Okay, I must have been in the do algebra. It will make you really understand what's going on by doing the algebra. Okay, so that's the Fejer kernel. So Fejer kernel is good. What about the Dirichlet kernel? Is it an approximation to the identity? What do you think? So the first thing is, does it integrate to 1? Yeah, because again, I have a bunch of exponentials, and the only exponential that doesn't integrate to 0 is when n equals 0. The coefficient in front of that is 1. Great, it integrates to 1. Okay, what about the contribution away from the origin? Is that going to be small? And the other one is it going to be non-negative? So can you find a value of x where this is negative? So do you think you can, look at this, do you think you can give me a value of x where this is negative?
probably because there's a shift in periodicity in the numerator versus the denominator.
So the numerator has a much greater period than the denominator. I'm not squaring things. So let's say I look at x between 0 and a half. The denominator is always going to be positive. So all I need to do is find one place where the numerator is negative. Okay, that's not a problem. Okay? So this is not going to be an approximation to the identity. It violates non-negativity. It gets worse. Right? The integral over regions, away from the origin doesn't tend to 0. This is not decaying. Okay? So things get really bad. Now the other thing is, of course, we should look and see what's going on near the origin. Near the origin, approximately how large does this look? So what would you say is the size of this near the origin? For all practical purposes, 2n. You should really say 2n plus 1. But yes. So near the origin, it's very large. So this is good. Right? So it has a lot of nice properties. It integrates to 1. It's very large near the origin. It's much larger near the origin than it is anywhere else. Near the origin it's of size n. Near other places, well, as long as I get a little bit away from the origin, the denominator is not going to be too bad. This is going to be at most 1. It's not going to be of size n. So it's really significantly larger at the origin than any other place. The problem is it's going to have sizable oscillations everywhere else. It's going to be negative. And that's going to cause a whole slew of problems. Okay? So again, I'm trying to emphasize the big picture, the key ideas here, and not the algebra. Where do you do algebra? At home, in private, where people don't see you doing it. Okay? So when you make all the algebra mistakes, no one has seen you doing the algebra mistakes. Okay? I'm not going to go through the proof now on why the Fejer series works. But essentially, we use the approximation to the identityness. And we use one of the most powerful tricks in mathematics. We multiply by 1. And so I will start the proof of the Dirichlet theorem. So Dirichet's theorem. So we'll assume f is differentiable at x naught, f in L2 of 0, 1, or we'll maybe do minus a half. Then Sn of f at x naught converges to f of x naught. So that's a wonderful theorem. And the way we get our hand on this is we can look at f of x naught minus Sn of f of x naught. This is equal to the integral from minus a half to a half of f of x naught times dn of, I want x naught. T minus x naught, maybe x naught minus t. No, it's t minus x naught. I'll do it this way. Minus the integral from minus a half to a half f of x. So I'm writing my stuff wrong. I will correct in just 1 second. So I'm going to do it this way. It's t minus x naught dt, put a minus here, and now, I'm sorry? Okay, so this is what I want. F of x naught dn of t minus x naught minus the integral of f of t dn of t minus x naught. The reason I can do this is what's the integral of dn of t minus x naught? It equals What does that integral equal? I think somebody said it. It equals 1. So even though the Dirichlet kernel is not an approximation to the identity, it still equals 1. So I'm just multiplying f of x naught by the number 1. I'm writing 1 in a very clever way. I'm writing 1 as the integral of the Dirichlet kernel. Why would I do this? Well, I'm following people who've already proved the theorem. No, I'm doing this because I know that I can write Sn of x as the convolution of f against the Dirichlet kernel. So this term I can represent as an integral. I want to write this one as an integral so I can combine things. And now I get the integral from -1/2 to 1/2 of f of x naught minus f of x times dn of t minus x naught. And so now it all comes down to understanding what's going on here. Well, fortunately, we have some understanding of what the Dirichlet kernel looks like. Right? So this is where we have to be very careful. We want to show that this integral is small. You look confused.
The f is probably right, but the f of t changed to an f of x.
Oh, thank you. Thank you, yes. So, thank you. So when t is close to x naught, this should be small. And then when t is far away from x naught, what should we be having? What do you expect will happen far away? So if t is close to x naught, we've got differentiability. This should be small. If I'm differentiable, I'm continuous. What about this over here, though? If t is very close to x naught, what's true about the Dirichlet kernel? It's like 2n plus 1. This is getting very, very large. So the problem is this is becoming very large when this is small. We need some way to control the contribution here. And this is where differentiability helps us, that this is so small when I subtract, it's even small when I divide by x naught minus t. And that's where the differentiability condition is coming in. We actually don't need the differentiability we talked about. We just need the Lipschitz condition. That's more than enough. Well, what about what happens as we go away from t being near x naught? We're now integrating the Dirichlet kernel. What about the integral of the Dirichlet kernel? So we have some difficulties here. So I just want to highlight just the key ideas of how you do the calculation. It is in the notes, it's in the book, except for one point which is glossed over. So near x naught, use differentiability. And what we have is we have f of x naught minus f of t divided by x naught minus t times x naught minus t over sine of pi x naught minus t times the sine of 2n plus 1 pi x naught minus t. Was it t minus x naught? T minus x naught. T minus x naught. And this should be t minus x naught. All right. So the minus sign isn't going to really matter. So what I've done is I've multiplied by 1 over here, and we've used, we know what the Dirichlet kernel is. So when we look at it like this, What do we know about this quantity here as x naught, as t approaches x naught? It's bounded by a constant. So if the function is differentiable, it's bounded by a constant. And in fact, if it's just Lipschitz, it's still bounded by a constant. That's all we need. What about this quantity over here? What's true about that? This is the most important limit in all of trigonometry. It's the sine of h over h. Right? What's the limit of sine of h over h? 1. This is also going to be bounded. What about this quantity here, the sine of blah? What does that look like? Less than or equal to 1 in absolute value. So in a small interval around x naught, this whole quantity here is going to be bounded. And so the contribution, if I'm going from, say, minus delta to delta, it'll be at most some constant times 2 delta. I take delta sufficiently small, and I'm going to have no problem from this. Okay? So because of the differentiability, the difficulty was the denominator here is what was killing us. When x became very, very small, we Taylor expanded both of them. We got a 2n plus 1 coming out. Because of the differentiability, we now absorb this into that ratio over there, and now the contribution from the remaining part stays bounded. Yes?
Why does differentiability allow us to do that again?
Well, because now this ratio over here is bounded. And so I'm basically saying the sine of pi x is essentially the same as pi x when x is small. That's what this ratio here is. That's a small constant correction. And now, by differentiability, this part is fine. And now, the reason this was blowing up when x goes to 0 was not the numerator, but the denominator. So this tells us that near x naught, the integral is going to be negligible. What about away from t naught? Away from t naught, what we can do is we can take absolute values, and we would have the integral of the absolute value of f of x naught minus f of t minus x naught times the absolute value of sine 2n plus 1 pi t minus x naught. And now I'm going to put the other factor over here, the sine of pi x over here. I'm going to just quickly go through the argument in the last minute. If I look at this ratio over here, when t is near x naught, because of my assumption of differentiability, this is fine. If I assume my function is bounded, or if my function is well controlled, then this is going to be bounded by a universal constant everywhere. So you can begin to see why we start making the assumptions we make about our function. I need differentiability at some point, and then away from that point, if I just have continuity, if I just have f as bounded, then everything is going to be fine. And now I'm left with integrating the absolute value of sine of 2n plus 1 pi blah. So we've got to just figure out what is the integral of the sine in absolute value. What you do is you split this into places where the sine is positive, and then places where sine is negative, and then sine is positive again. We keep splitting it up like this. Approximately how large is the window where sine is positive? I have the sine of 2n plus 1 pi. So about how much does t get to move before I end my window being positive and enter a window where I'm negative? Approximately how much does t move? So okay, I don't care about the pi's and the 4's. I care about something of size 1 over n. Every time this argument increases by 1 over n, roughly, I've gone through a whole cycle. So each of these cycles is going to have a width of size 1 over n. When you take, I can now drop the absolute values in each of these intervals and then just sum all their contributions. And now I'm going to have the integral of sine as cosine. But I'm going to have an n here, so when I integrate a sine, I'm going to get an n in the denominator. And I'm going to get basically the difference in cosines at those 2 points. And this is the point that's kind of glossed over in the book. I'm multiplying by the length of the interval. So that's the part you've got to look at very carefully. I have on the order of n intervals. If I don't have this weighted by an extra length of the interval, I'm dead. All right, so I'll let you think a little bit about that. This is, a good place to end. So a lot of technical stuff today.